about anomalies, generalized symmetries, and compactifications.
Okay. Thank you for the introduction, and thank you for the organizers for inviting me to speak. So I'm going to tell you about some work that I did in collaboration with Orsela, Gabi Zafrir, Emily Nardone, and Yunqin Zheng. And so the idea is that we try to understand the relationship between various concepts in quantum field theory. So on the one hand, we have generalized symmetries and anomalies, and on the other hand, the compactifications of quantum field theories. So we have seen since like this paper by Gaiotto, Capuzzi, and Saber-Willett, by now 10 years ago, that there's been a major revolution in the concept of symmetry in quantum field theory, and many new generalizations of symmetries have been proposed. When we study quantum field theories, of course, it's very useful to have symmetries because they allow us to constrain especially the non-perturbative dynamics. For example, via selection rules for correlation functions of operators, and anomalies which are invariant along the RG flow. So some of these generalizations that will appear in my talk are higher form symmetries, which act on extended operators, higher group symmetries, which roughly speaking mix higher form symmetries of different degrees, and non-invertible symmetries, which generalize usual symmetries because now we don't have a group-like fusion rule. So on the one hand, we have symmetries. On the other hand, what I want to talk about is compactification, which is another powerful approach to investigating quantum field theories. So the idea, in general, is the following. It was actually explained a little bit also by Dario in his talk. So you can consider a quantum field theory in some number of dimension, capital D, and you can think of compactifying some of the space-time directions. So for example, lowercase d directions are compactified with this compact manifold C. In the process, we should also specify some other extra data. This could be, for example, fluxes or anomalies for global symmetries. And this is the key point is that we can think of this compactification as triggering some RG flow that now interpolates between different number of dimensions. Because now we introduced a scale, which is the scale of this compact manifold. For example, if it is a circle, it could be the radius. And we can flow to energies which are much smaller than the inverse of the scale. And this is going to give us an effective lower dimensional theory. So there has been a lot of work in this direction, which I'm not going to review, but let me at least say, like, the philosophy is that it is useful to consider this compactification because oftentimes we can infer many non-trivial properties of the lower dimensional quantum field theory just in terms of some geometric considerations of the compactification that we did, and the properties that are known of the higher dimensional theory, because maybe this was engineered, I don't know, in string theory or with some other construction. I also want to make a quick comment on supersymmetry. So what I'm going to tell you about in principle applies to any type of quantum field theory, but I will mostly consider supersymmetric theories because, as we know, we have more control of them. And in fact, these compactifications have been understood a lot for supersymmetric theories. So for me, they are kind of like a nice laboratory to test the ideas that I want to explain because we can use this additional tool to check them. So what I'm interested in is the interplay between symmetries and compactifications. And this can already be subtle for ordinary symmetries, what we would call zero-form symmetries, because of two phenomena that might happen. So naively, you might think that the symmetries of the higher and the lower dimensional theory are the same, but this naive expectation can be spoiled in two ways. So one thing that can happen is that there are accidental symmetries, and we know many examples of symmetries that emerge along the RG flow, and this can also happen in these RG flows across dimensions. So when this happens, the lower dimensional theory has a bigger symmetry than the higher dimensional one. In some cases, this can be understood from the compactification because maybe some of these emergent symmetries are related to isometries of the compact space. For example, if the compact space is a two-sphere, you would expect an SO3 additional symmetry. Or something that can happen is that some symmetry end up acting trivially at the end of the RG flow. So in this case, the lower dimensional theory has less symmetries than the higher dimensional one. This other possibility can actually be ruled out with anomalies, because anomalies are RG invariant, so they are invariant along this flow. And if an anomaly is, for some symmetry, is non-trivial, then there must be some degree of freedom also in the lower dimensional theory that transforms under this symmetry and accounts for the anomaly.
It could be a gapless sector.
Yeah, of course, yeah. Actually, most of the examples that I will consider the lower dimensional theory will be an SCFT, so...
but it could be a TQFT that transforms under the symmetry.
Yeah, of course, yeah.
Decoupled sector.
Yeah. So the question that I would like to ask is a bit more general, although I will try to answer it in some particular context. So this is about ordinary symmetries. Instead, I would like to understand what happens to generalized symmetries and various types of anomalies under this type of compactifications. So let me start with some review of basic concepts in generalized symmetries, since this is a topic that's maybe a bit different from the one of this workshop. So the key idea that was proposed in this paper is that we should think of symmetries as associated to topological operators. This is something that already Michele yesterday told us about. Here I'm being a bit more explicit by considering some concrete example, which is easy to explain. So if you consider an ordinary U1 symmetry, you're going to have a conserved current J associated to it. And the topological operator is obtained by integrating the star of J over a codimension 1 manifold. And we exponentiate this with some group theory parameter alpha. This is now a U1 parameter. And this object is topological just as a consequence of the conservation equation. So you can think of placing it on some manifold M and deforming it continuously to some other manifold M prime. Then you view this M and M prime as boundaries of a d-dimensional manifold. And you just do some simple manipulations to show that the defect has been left invariant. And the interpretation of these defects is that they implement the action of the symmetry on operators. So now you can think of taking some operator phi at some position x bar that transforms under the symmetry. You encircle this operator with the topological defect. Now you start shrinking the defect. As long as you don't cross phi, the defect is topological, so nothing happens. But the moment you cross phi, you're going to pick up a phase, because now it's like you added a source for this symmetry, so the conservation equation is modified in this way. You might think this is like a trivial way of rephrasing things that we already know about symmetries, but the point is that thinking about topological defects is useful to find many generalizations. So these are the ones that I was mentioning before. So you can have higher form symmetries by now relaxing the assumption that the topological defect is of codimension 1. So if it is of codimension p+1, you talk about a p-form symmetry. That's why I was saying that ordinary symmetries are zero-form symmetries. Then you can have two-group symmetries, which refers to the situation in which, in your theory, you might have a zero-form symmetry G0 and a one-form symmetry G1, but the full symmetry structure of the theory is more complicated. It's not just a direct product. And finally, the non-invertible symmetries occur when, if you try to compose two defects associated to two different symmetry transformations, alpha and beta, you don't get the defect for alpha times beta. So you don't have this group-like fusion rule, which in particular tells you that some of these defects, some of these transformations do not admit an inverse element. About these higher form symmetries, I told you that they are generated by codimension p+1 topological operators. And I told you before that these defects essentially measure the charge of some object by encircling it. So if now the topological defect is of higher codimension, then it means that the object that transforms under the symmetry should also be extended, because they should link with it. For example, in 3 dimensions, for a one-form symmetry, the defect that generates the symmetry is a line, and a line can link with another line in 3 dimensions. So in general, a one-form symmetry will act on line operators. And these symmetries, these higher-form symmetries, can be found in very simple models. For example, some of these higher-form symmetries that I will need later appear just in the Maxwell theory. So in Maxwell theory, you have a field strength. So the notation in my talk is that I will use lowercase letters to denote dynamical gauge fields, while uppercase letters are background gauge fields. So in Maxwell theory, if you just consider the field strength, you can view it as a conserved current, and the conservation equation is just the equation of motion. But now the star of f should be integrated over a codimension 2 manifold, because f is a 2-form. And so in this language of the higher form symmetries, we will say that this current is generating an electric 1-form symmetry, which is the symmetry acting on the Wilson lines of this theory. Similarly, if you consider the star of f, you can also view it as a conserved current, now just by the Bianchi identity. And again, this is going to generate a higher form symmetry, which is now of degree d-3. And this is what we usually call the magnetic symmetry. So in 3 dimension is a 0-form symmetry. In fact, it's what has been known for a long time as topological symmetry, also 3-dimensional theories. In 4 dimensions, which is a setup that I will consider, it's a 1-form symmetry. So 2 important concepts for me will be the anomaly polynomial and the anomaly theory. So an anomaly, we know it's an anomaly for a global symmetry. It's a failure of the partition function in being invariant under a background gauge transformation. So you compute the partition function of your theory as a function of a background field for some global symmetry. And if you perform a gauge transformation, then the partition function is not invariant if you have an anomaly. So you pick up some exponential, which is your anomaly. And if you're working with continuous symmetries, this anomaly can be efficiently encoded in the so-called anomaly polynomial, which is essentially a theory that now lives in 2 higher dimensions. And so the action of this theory is this ID plus 1, is what we call the anomaly polynomial, and it's related to the anomaly by the usual descent equations. So this applies to continuous symmetries, in particular in even dimensions. But if you work with finite symmetries, you don't have the anomaly polynomial, but you have something that is very related, which is what is usually called the anomaly theory. So the anomaly theory leaves only 1 higher dimension, so on this manifold, yd plus 1, which is such that its boundary is your d-dimensional space-time. And the anomaly theory can be defined also for continuous symmetries. Essentially, you just use the second one of the descent equation to find it. But it can also be defined for finite symmetries, and it has the property that under a background transformation, it's also not invariant, and basically the extra piece that you pick exactly cancels the anomaly of your theory. So if you want, you can consider the product of your partition function and the one of the anomaly theory, and you get an object which is fully invariant. Now, if you notice here, I'm writing the partition function of the anomaly theory just as an exponential. And the reason is that both in the anomaly theory and in the anomaly polynomial, only appear background fields for global symmetries, which are non-dynamical. So these theories are actually classical theories. They don't undergo any RG flow. And this is what leads to an important concept, which is the one of Toft anomaly matching, which tells us that anomalies are invariant along the RG flow. So even though your QFT might have a very complicated RG flow, the theory is this anomaly theory that captures its anomaly is instead completely classical. So what happens to these anomalies under compactification? Yes?
So for the continuous symmetries, then these anomaly polynomials make sense only for even dimensional theories.
Yes.
So what you said also makes sense for odd dimensional theories?
The anomaly theory, yes, can be on any, yes, in any dimension. In fact, what I will mention it later. What we did in our work was like in 5 and 3 dimensions. So that's also why it's interesting, because usually when you do compactifications between odd dimensions, you don't have anomalies as a tool for continuous symmetries, but you can still do finite symmetries. So let me start from the anomaly polynomial under compactification. Well, now the idea is quite simple. I just told you the anomaly polynomial is invariant along the RG flow. And so in particular, for this RG flow across dimension, you should expect to be able to relate the anomaly theories of the higher and lower dimensional theories. In fact, this is something that has been understood a long time ago. So the idea is that the anomaly polynomial of the lower dimensional theory is obtained by taking the one of the higher dimensional theory and integrating it on the compact space. And later on, I will show you some explicit example of how we do this compactification. So, as I told you, this is something that has been in this case, I'm also making an assumption for simplicity. I'm assuming that this compact space C doesn't have any boundary. Otherwise, you would have contributions also from the boundary. So as I said, this idea has been tested extensively, especially for supersymmetric theories. And so the question is, what about finite symmetries? Well, the answer seems obvious because I told you that both the anomaly polynomial and the anomaly theory are RG invariant. And so you would expect that, you should expect that you should be able to do the same also for the anomaly theory. And that's in fact something that we try to understand in this paper with Orr and Gabi. So again, for this, it's crucial to assume that C is boundless because remember, the anomaly theory lives in one higher dimensional manifold whose boundary is your space-time. And so to be able to preserve this property both in higher and lower dimension, C must be boundless. But once you assume this, you can just obtain the anomaly theory in lower dimensions from the one in higher dimension by doing explicitly this integration over the compact space. So what we did in our paper with Orr and Gabi was to try to check explicitly this idea. So as I said, this applies generally, but we consider a particular setup, which is the one of compactifications of 5D n equal 1 as CFTs on Riemann surfaces. And in this compactification, you can preserve n equal to 2 supersymmetry in 3 dimensions with a topological twist. And this compactification, we have been studying them for quite some time with Orr and Gabi, and now we have many results on them, because thanks to supersymmetry, there are various checks that we can do to study them. And so we just imported these results to check explicitly this idea of the compactification of the anomaly theory, and it seems to work. Any question on this? Okay, so in the paper, indeed, we have many examples of this type of computations, but for this talk, I don't want to go into these details, and instead I would like to tell you something about the second paper that we wrote, in which we study what happens to the generalized symmetries under compactification. Yeah, they're for finite symmetries. They, well, they could be both zero form and one form. It depends on the theory. For example, we consider the cyber theories. So you can, for E1, you also have a one form symmetry. So you can also study that. So in general, they are either finite symmetries or like for continuous symmetries, but using some discrete class, like Stifel-Witten class and so on. It depends what you're doing, because in this compactification, you turn on fluxes for the symmetry. So I cannot tell you like in general what happens, but case by case, you can figure it out. Okay, so let me move to these generalized symmetries, and let me also give you a quick review of some of these symmetries, especially the ones that I will consider in my setup. So two-group symmetries, I told you before, roughly speaking, refer to the situation in which you have a zero form and a one form symmetry, but do not form a direct product. So to explain this better, let me give you an explicit example of a theory in which this happens. And this is just a QED in 4 dimension with an F Dirac fermions. So you can split the Dirac fermion in pairs of Weil fermions. And here in this table, I'm just summarizing how these fields transform under the various symmetries. So U1G is the gauge symmetry. Then you have an axial symmetry under which psi and chi have the same charge. And then you have independent SU and F symmetries for each of these two sets of fields. Now, when you start computing anomalies in this theory, you first find this type of anomaly. So, well, this is not inequality, it's an inclusion. It's one of the anomalies that you can find, which is linear in the gauge symmetry, in the C1 of the gauge symmetry, and, well, quadratic in the field strength of the SUNF flavor symmetry. From this anomaly polynomial, you can extract how the conservation equation of the current for these flavor symmetries is violated. And you find this type of equation. On the right-hand side, you have the dynamical field strength, but also the background field for these two, one of these two symmetries. And because of this, you can understand that this anomaly, well, you can think that this anomaly is not having some dramatic consequence on the symmetry, because on the right-hand side, of course, you're allowed to turn off this background field. So this equation is not telling you that the symmetry is broken. But there is still some consequence of this anomaly, which has been investigated in this paper by Cordova, Dumitrescu, and Intrigator. So to detect that, you have to turn on not only the background gauge field for the SUNF flavor symmetry, but also the background gauge field for the U1 magnetic one-form symmetry, which I will always call B. So every time you will see B in my slides, that's the background for the magnetic symmetry. So this is how they couple in the action to the currents. And by using this equation, you can show that if you do a background transformation for the flavor symmetry, then the action is not invariant, which is a manifestation of the anomaly. But you can make it invariant if you also require that B transforms when you do a zero-form symmetry transformation. And it should transform in this way. So these two equations are essentially the hallmark of a two group. And so the idea is that if you have turned on a background field for the one-form symmetry, and you do a transformation for the zero-form symmetry, then also B should transform. It cannot remain invariant. The other type of symmetry that I mentioned is the non-invertible symmetry. And again, let me give you an example that will be relevant for me. This non-invertible symmetry actually appears in the same theory that I considered in the previous slide. But now we consider the U1 axial symmetry. In this case, there is again a mixed anomaly between the axial symmetry and the gauge symmetry, but now it's quadratic in the gauge symmetry. And because of this, the violation of the conservation equation is actually more dramatic, because now on the right-hand side, you only have dynamical fields, which are not allowed to set to zero. So this anomaly is really telling you that the axial symmetry is broken. In fact, the old lore behind this type of anomaly, which is known as ABG anomaly, is that the axial symmetry is broken to some finite subgroup whose order depends on the anomaly coefficient k. But what has been shown more recently is that actually we can retain more symmetry transformations inside U1 rather than just these decay transformations. And these are rotation by any rational angle. But the price that you have to pay is that now these transformations are not invertible. So this is essentially the setup that I will consider for the compactification. Let me reiterate. So I will consider four-dimensional theories that have a U1 part of the gauge group to which we can associate a U1. Yes?
So, in the paper produced by
Yep.
so the transformation is non-invertible. Is this a definition of non-invertible symmetry?
The definition is essentially this one. So what you can, I will show you explicitly what are the...
They don't compose...
Exactly, yes. Oh. I will show you later explicitly what are these defects in the case of this symmetry. And exactly, and they don't obey... exactly.
Which then implement a symmetry.
Exactly. Exactly. Yeah. But I will show you more about this later, so maybe it will become clearer. If it's not, you can ask me again. Yes. Okay, so I was saying the setup is the one of theories with a U1 gauge group, at least a U1 gauge group, and a U1 magnetic one-form symmetry. And also to simplify things, I will assume the zero-form flavor symmetry to also be abelian. And again, this could be any theory, but the prototypical example that we considered is the minimally supersymmetric SQCD with UNC gauge group and NF flavors. So, too much. In this type of theories, you can have various anomalies, also mixed anomalies between the U1J and U1F. So, for example, you can have an anomaly which is just cubic in the flavor symmetry. This is what we call an 't Hooft anomaly. And it just represents an obstruction to gauging F, because again, this conservation equation can be restored if you turn off the background F. But if you want to gauge the U1F symmetry, then this field becomes dynamical, and so the current is really not conserved. But I'm not interested in this type of anomaly, so the one that I'm interested in is the one for the 2 group that I showed you before. So the crucial thing to remember is that it's linear in the gauge symmetry. And again, it tells you that here the flavor symmetry is not conserved, but if you turn on the background for the magnetic symmetry, then it should also transform under the zero form symmetry. And lastly, there is this ABG anomaly, which is now quadratic in the gauge symmetry. And it tells you that the flavor symmetry has an invertible ZK subgroup, but also a non-invertible Q mod Z subgroup. Okay, so the question is, what happens to these generalized symmetries when we perform a compactification? In our paper, we consider 2 types of compactification, on an S1 to 3 dimensions and on a 2-sphere to 2 dimensions. But in this talk, I will only focus on the S2 compactification because it's the more interesting one. And again, the results are general, but in the paper, we studied one particular type of compactifications of supersymmetric theories. So you can start in 4 dimensions with an n=1 theory. And when you do the compactification on S2, you can do a topological twist which preserves 0,2 supersymmetry in 2 dimensions. So this is a type of compactification on which like many people worked in the past, and so we know enough about them to try to test our ideas. So let me tell you a little bit about how these compactifications work. An efficient way to study these compactifications, at least if you're trying to compactify a 4-dimensional Lagrangian theory, which is what I'm going to do, is to use the partition function on a 2 torus times a 2-sphere. So for a Lagrangian theory, this partition function can be computed with supersymmetric localization, and schematically it looks like this. So you have an integrand. I don't really care for this talk about what is the integral, but conceptually it's important to remember that it's completely specified once you give me what is the Lagrangian of your theory. Then you have an integral, which again, it's not relevant for me. The part that is more relevant is this summation. So these discrete numbers are magnetic fluxes for the gauge symmetry through the 2-sphere. So in general, this is a vector whose dimension is the rank of the gauge group. And you can parameterize it by picking some maximal Cartan subgroup of G. And then you will have a flux for each U1 element in this subgroup. So that's why in this formula, I say, so these fluxes should obey some Dirac quantization condition. So that's why they take values in the co-weight lattice of the gauge group. The crucial observation that has been made in this paper is that if you pick one particular element in this sum, then you get an integral which you can immediately recognize as the elliptic genus of some 2D 0,2 Lagrangian theory, which can also be computed with localization. It has been done in these papers. So what is the interpretation of this result? Well, the interpretation is that if you take your 4D theory, you compactify it on a 2-sphere with this topological twist, in general, you might not get just a single 2-dimensional theory, but a direct sum of many 2-dimensional theories. And what's useful for me is that using this partition function, for each of these 2D theories, I have an explicit matrix integral expression for the elliptic genus, out of which, if I know the rule of the game of localization, I can literally read off the content of the 2D theory. So the content as vector multiplets, chiral multiplets, Fermi multiplets, and so on.
So isn't it an infinite sum?
In principle, it is. So something that they showed in this paper is that in general, it's gonna truncate.
Oh, but the one you twist, I see.
Yeah. And then you can add some additional requirement on the R symmetry that you use to twist, and that can lead to further simplifications. Yes.
Can I think about this sum as that you're turning on fluxes on the S2, so you're essentially drafting the operator of the.
This is on the next slide.
Okay, so you
Yeah.
get the decomposition.
Yeah, exactly. Yeah. This is exactly what I was gonna say. Is that? Yes.
When you go, if I remember correctly, when you go from 3 to 2, and
Yes.
you reduce the superformal index from 3 to 2,
Yeah.
this direct sum of 2D theories makes the entire reduction a little bit not shaky but difficult to do. Instead, from 4 to 2, everything goes smoothly.
Why shake? So you're thinking about you take S2 times S1 in 3D with a topological twist on S2 and you reduce on the S1.
No, sorry. It's
No,
not
what?
a topological twist. That's
It-
with a
it-
superconformal index.
Yeah. But there,
There's no topological twist. So
you have to be careful about how you do the reduction, but in general, like the summation and so the integral is on a unit circle. Then you have a summation. If you're careful about how you do this limit, it's going to become a complex integral in 2D, which is what you have for the S2 partition function in 2 dimension. So in that case, you don't have subtleties. Like it might seem weird to have like a summation in 3D that disappears in 2D, but that's what actually happens. Yeah, I can tell you more later. So yes, my next comment was gonna be about the defect for the magnetic one-form symmetry. So remember, this is a one-form symmetry, so it's a codimension 2 defect, which in 4D is 2-dimensional. And what I can think of doing is to wrap this defect completely on the S2 that I'm using for the compactification. Then it's going to become point-like in 2 dimension. And so it means that it's still of codimension 2 in 2 dimension. So it's going to be associated to a one-form symmetry in 2D. But yeah, there is this story of the composition, which I didn't want to tell you about. But in general, when you have a d-dimensional quantum field theory with a d-1 form symmetry, then you have this decomposition in disjoint universes. This is exactly what's happening here. So what I want to say is that if you wrap this defect over the S2, then you get just the exponential of the gauge flux. So you can think that of each of these 2D theories that I have, these are distinguished by the charge under this one-form symmetry. So the crucial observation is that if now I focus on one particular element of this sum, then I completely lose the one-form symmetry, because then this defect gamma becomes just a phase, essentially. So if I go to one 2D theory that corresponds to one particular value of the gauge flux, there the one-form symmetry acts completely trivially. And so because of this, all the generalized symmetry structures that I told you about before are completely lost when I focus on one of the 2D theories, because they relied on the existence of this magnetic one-form symmetry. So this sounded a bit disappointing, but actually what we showed in this paper is that there is still an imprint of these generalized symmetries that you have in 4D on the 2-dimensional physics. And in particular, what I'm going to show you is that it can manifest itself either as some symmetry breaking pattern of the flavor symmetry or some additional Tuft anomalies. It's, yeah, I mean, this is, it's a bit technical, but if you, okay, I said that I didn't want to talk about the integral, but if you're more careful about it, you will see some pole structure. And what these guys showed is that if the flux essentially is too big, then this integral is not providing enough poles, and so the integral is just 0.
Some of the universe is empty.
Yes, because the partition function is 0. Yeah. Yeah. No, absolutely. No. So each of these universes will have a different Lagrangian. So, yes.
What do you mean by each universe has its own Lagrangian? All operators universe is zero, right?
Yeah, it's exactly that, because if you fix one term in this sum, you're fixing the gauge flux, and the exponential of the gauge flux is the topological defect that measures the charge. So in each of these universes, everything has the same charge under the one-form symmetry. Yeah.
also put all the two-dimensional defect in two dimension and you get a -1 from symmetry. So you have the possibility of observing on some theta angle. Are you putting all theta angles to 0?
Yeah, I think so. I haven't thought about that. So I think yes.
So do you expect similar splitting in universes if you have if you instead compactify to 3D on a circle and you have a two-point symmetry?
So 2 for symmetry is.
So instead from 4D compactify a circle to 3D.
I think so. Yes. Yes. I haven't looked into it, but in principle, yes. Every time you have a d-1 for symmetry, it should decompose. More questions? Okay. So let me show you one way to derive this thing that I told you, that the generalized symmetries imply some 't-Hooft anomalies or symmetry breakings in 2 dimension. And so this is maybe the simplest approach to explain it, but it has some problem that I will discuss in the next slide. But let's try to go with it for the moment. So what you can do is take the anomalies that I showed you before were associated to the generalized symmetries and do this compactification of the anomaly polynomial. So now I can be a bit more explicit on how this is done. Simply, every time you have, in a term of the anomaly polynomial, the first Chern class of the gauge group, you can integrate it over the S2 and get the gauge flux. And similarly, you can get a flavor flux if you compactify the C1 of the flavor symmetry. So let's try to do it for the anomaly for the two-group symmetry. So this is one term, but it's going to produce two terms depending on whether I'm integrating the C1 of F or the C1 of G. If I integrate the C1 of F, then I pick up the flavor flux, and I have this mixed flavor gauge symmetry anomaly. And so this is an anomaly that's it's similar to it's an ABG anomaly. It's telling you that the flavor symmetry U1F is broken to some finite subgroup. And now the order depends not only on kappa, that was the 4D anomaly, but also on the value of the flavor flux. Or what you can do is to integrate the C1 of G. So this is going to give you a pure 't-Hooft anomaly for the flavor symmetry that wasn't present in 4 dimension. Or if there was a 't-Hooft anomaly in 4D, this would add up to it. And again, the coefficient of this anomaly depends not only on the 4D anomaly kappa, but also on the value of the gauge flux. You can do the same exercise for the anomaly for the non-invertible symmetry. Again, in principle, you produce two terms. But the first one, obtained by integrating the C1 of F, would be a pure gauge anomaly in 2 dimensions. So this is telling you that if you have this type of anomaly, when you do the compactification, you cannot turn on a flux for the U1F symmetry. Otherwise, you would have a gauge anomaly in 2D. So MF has to be set equal to 0, but you can have a gauge flux. This is going to give you again an ABG anomaly in 2D, which again leads to a breaking of the flavor symmetry. But now the order is this other anomaly coefficient and the gauge flux, while here it was the flavor flux.
Sorry, the flavor flux you can set to 0. The gauge fluxes you cannot decide, right? You have to sum of all.
The gauge flux is going to be fixed once I pick one of these 2D theories. Remember, like we had these universes, and
You have to sum of all the allowed ones.
yeah, but if I take like one of these 2D Lagrangian theories, then it will have an anomaly, which is this one. Then I have many of these Lagrangian theories, so each one will have a different value of this anomaly depending on the gauge flux. This is the idea.
So, are you thinking of having a projector or something like an operation?
Yeah, you can also do that. Yeah. Yeah. There is also another.
What guarantees electromagnetic duality for Maxwell theory?
Yeah.
Otherwise, and that is due because you want
Yeah.
you want electric and you want magnetic at the same time.
Yeah.
So when you break the sum, you know that you're making something which will break electromagnetic duality.
But luckily, there's another way to pick one particular element of the sum, which is gauging a subgroup of the magnetic symmetry in 4D. This is going to get rid of some of the magnetic fluxes. So you can focus on one particular one if you do this thing and also introduce some holonomy for the magnetic symmetry. So this is something that you can formalize better.
This is the operation.
Yes.
When you pick up
Yes, exactly. Okay, so as I was telling you, there's a major problem with what I did in the previous slide, which is that if you remember, I told you that you can do this procedure of integrating the anomaly polynomial because anomalies are G invariant, but this is not true for anomalies for gauge symmetries. And the reason is very simple, because these terms in the anomaly polynomial involve gauge fields, which are dynamical. So you don't expect this term to be invariant along the RG flow. In fact, I mean, once you flow to the infrared, you don't even know like what it means to have a gauge symmetry, right? However, the expectations that you can predict by integrating the anomaly polynomial turn out to work. So what I mean by this is that, as I told you, I can get explicit two-dimensional Lagrangians using the partition function. So I can independently compute the anomalies in this Lagrangian and verify that they reproduce exactly the one that I obtained by integrating the anomaly polynomial. So these are two independent computations that seem to match. So the question is, how is it possible that what I did in the previous slide works? And the resolution is that these gauge anomalies were associated to generalized symmetries in 4 dimensions. And symmetries are instead something that, in general, is invariant along the RG flow, unless you are explicitly breaking it or it's trivializing. So what we did was to essentially recover these 2D observations, but from the perspective of the generalized symmetries, so without any need to refer to the gauge anomalies. And so this is the proper way to justify what I did before. How much time do I have?
20 minutes.
20 minutes, okay. Okay. So this is what I'm going to do next. Essentially, I will recover the same results, but using this other approach. For example, one thing that you can do is working with the background fields for these global symmetries. So let me try to recover this result. So let me repeat it. So if you have a 4D theory with a two-group symmetry with a coefficient kappa, and you compactify on the two-sphere with a flavor flux, then in 2 dimensions, the U1 flavor symmetry is broken to Z kappa times MF. So how can we recover this? Well, essentially what you do, you take the two-group transformation. Remember, the background B for the magnetic one-form symmetry has to transform when you have a two-group symmetry, and you just integrate that relation over S2. So you get a transformation for phi, which I defined as the integral over S2 of B. Now, this phi has an interpretation. If you exponentiate it, it's just an holonomy for the one-form symmetry, which is something that you are, of course, allowed to turn on when you do the compactification. But if you change the holonomy, you're changing the theory, because you're literally doing another compactification. So the two-group tells you that you should have this transformation, but this transformation should leave the holonomy invariant. And so if you require this, this is going to constrain the possible transformations for the zero-fold symmetry, which were labeled by this parameter lambda. And in particular, what you find is exactly that the only transformations that you are allowed to do are those for this finite subgroup that I was telling you about. I also told you before that if instead you compactify a two-group with a gauge flux, you get an 't anomaly. I'm not going to review this because it's very similar, and also actually it's not new because it was already discussed in the paper by Cordova, Dumitrescu, and Triligator. Yeah.
Breaking of U1F into D.
Yeah.
From the point of view of D is like an MPJ anomaly, right?
Exactly. It's what I was showing you before. So before.
I was wondering, I don't know if there is a story similar to what D that becomes
No, in 2 dimensions, that's not happening. Like, you still have to dress the defect to make it topological, but the dressing is not, it doesn't imply that it becomes non-invertible, so. Exactly. Exactly.
Why?
Uh,
Is there a quick way to understand why?
well, I guess it's because, this dressing is done with topological quantum field theory, which in 4D is 3-dimensional, it's gonna be 1-dimensional, so it's a very trivial dressing. Yeah.
1D to TFT are just numbers.
Yeah, exactly. So 1D TQFT are just numbers. So
you don't enlarge the symmetry at the
Exactly. Yes. Yes. Yeah. Because when you do it in 4D, I'm gonna show, I think, in the next slide, but in 4D, you have to put this very non-trivial TQFT that lives on the defect. And so that's what makes it non-invertible. Yeah. Yeah. Yes, essentially. Yeah, I'm gonna actually discuss this a little bit more in a moment. So this is exactly the approach that I would like to use to derive the other result. So if you compactify a non-invertible symmetry with coefficient k on S2 with a flavor flux, you get again a symmetry breaking. So for this, I will use indeed the perspective of the topological defects. So here I can be more explicit on this. Let me start with a warm-up. So let me take the defect for the invertible ZK subgroup, which is constructed as follows. So if you remember at the beginning, I told you that the defect is constructed by exponentiating the star of f. And the defect was topological because this star of f is equal to 0. But now this star of f is not equal to 0 anymore. And so that's why I am dressing this defect with this additional term. So with this additional term, I can make a defect that is completely gauge invariant, because this was the violation of the conservation equation, and it implies that the D of all of this bracket is equal to 0, which is what I needed to show that it is topological. And let me also stress that it is gauge invariant, because essentially I'm dressing it with a Chern-Simons theory that has a properly quantized Chern-Simons level. So what I can try to do initially is to wrap this defect on the S2 that I'm using for the compactification and an S1 in the remaining two directions. So let's see what happens. So essentially, you can do explicitly the integration of this part over S2. And what happens is just that when you integrate the A, you're going to pick up the gauge flux. So that's why I get this expression. So this, for the defects, are reduced to these two-dimensional defects, which again are defects that just generate an invertible ZK symmetry. So this is fine. But I told you that in 2D I expect a larger symmetry, ZK times mg. So in this way, I'm just obtaining some of the transformations of the group that I expect. Because remember, this was like the AVG anomaly in 2D. The coefficient was k times mg and not just k.
Sorry, I don't understand from the first to the second line. Star JF is
Yeah, this I'm abusing a bit the notation. This is the 4D one, this is the 2D one. So yeah, sorry.
Can you explain why there is a factor of 2 here?
Well, because you can integrate either this or this, right? Yeah, it's just that. Okay, so how do we get the remaining transformations? Well, to do that, you have to consider now the defects for the non-invertible symmetry. Morally, these defects are constructed in the same way. So you cannot just take the star of f because this is not conserved. You have to dress it with something to get a topological defect. But now the dressing is way more complicated. You have to add this theory, this A n comma p theory, which was studied in this paper. And without going to the details, so this is just a 3D TOQFT that has these properties. It has a Zn one-form symmetry, and which has a self-anomaly that is labeled with P. And this anomaly is exactly the value that you need in order to soak up the gauge anomaly. So when you do this dressing, it has been shown in the papers that I cited before, the defect is topological, it's still gauge invariant, but now it's non-invertible because you added this non-trivial TQFT on the defect. Now I want again to wrap this defect on the S2 and see what I obtain. And to do this, I want to use the fact that these TQFTs, they all admit a Lagrangian description in terms of some abelian Chern-Simons theory. For example, for p equal to 1, this is just a U1 level n Chern-Simons theory that has this action, to which I should also add this term that is the coupling with the one-form symmetry. But such a Lagrangian description can be found also for any p. It's just more complicated. You have more U1 groups and so on, but the idea is the same. And so you can use this Lagrangian description to do explicitly the integration of RS2. Again, every time you integrate the D of some gauge field, you're going to pick up some flux. And the result is the following. It might seem a bit complicated, but it's just telling you that you have defects for a ZK times mg symmetry, because this number is always integer if you have this condition. And so in two dimension, you get these defects so the 4D non-invertible defects reduce to invertible defects for the entire ZK times mg symmetry in 2D. So the crucial point here is that if I want to recover this symmetry that I wanted, I cannot just focus on the invertible symmetry in 4D, but I have to consider all the defects, also these Q mod Z defects.
So the message is you should start, you have to consider full non-invertible symmetry.
Yes.
And it generate the full invertible symmetry.
Exactly. Exactly. Yes. Yes.
Sorry, I'm just repeating what you said, but just
Yeah, exactly. That was my point. So initially I was looking only at the invertible ZK defect, and I showed you that they reduce to ZK defects in 2D, but they are not enough to explain the entire symmetry that I'm predicting. So this non-invertible symmetry is really crucial to obtain the...
I'm a bit of an outsider, so maybe I'm making very naive questions. So you are saying that a non-invertible symmetry in dimension can become an invertible one in lower dimension
well,
certain conditions.
This is a particular... It's not a general statement. Here I'm considering some very particular setup, which is this...
Working here, I'm asking. Do you think it's a more general
it might work for maybe any ABJ anomaly in any dimension. So it's very crucial that it's an ABJ anomaly. So, yeah.
Sorry, not understanding the dimension of the room, because I mean, for D you have infinitely many defects, and to D you have finitely many ones. So is that some of them trivialized?
Yeah, there's a computation that you do here. So let's see if I can explain it with the example for p equal to 1. So when you integrate over S2, you pick up a flux. Okay, no, I cannot explain this, but trivialize, yes. Every time this condition is not satisfied, they all trivialize. Yeah. It's just a result of the computation, so which is a very simple computation.
So some of them still are non-invertible in 4D, becomes invertible.
Exactly. Yes. Okay. I think this is actually all that I wanted to tell you, so I will conclude. So let me first summarize what I told you about. So the first thing that I discussed is this idea of the integration of the anomaly theory over the compact space when you do a compactification, which indeed it's nice because now it can be applied to finite symmetries in any number of dimensions. So now you can go from even dimension to even, but also even to odd, all the combinations that you can think of. And we check this for these 5D to 3D compactifications of supersymmetric theories, but the idea is applicable to any type of compactification. So it's a new tool that you can use to study them. And in the second part, instead, I discussed what happens to generalized symmetries under compactification. But let me stress that it was in this particular setup in which you have a U1 gauge group that has an associated U1 magnetic one-form symmetry, and also U1 flavor symmetry, and we compactify on S2. And what I showed you is that this generalized symmetry is trivialized in 2D, but there is still some imprint. So in particular, if you compactify to group with a flavor flux, you get a symmetry breaking. If you compactify to group with a gauge flux, you get a 't Hooft anomaly. And if you compactify non-invertible symmetry, you cannot turn on a flavor flux, otherwise you will get a gauge anomaly in 2D. But you can turn on a gauge flux and you get a symmetry breaking in 2 dimensions. Let me also briefly mention something that I skipped in this talk. So as I told you, we also studied compactification on a circle, but there the story is a bit boring because in this setup that we consider, we just did an S1 reduction without any twists and other things. And if you do this, like again, everything trivializes completely. So you need to do some fancier stuff. And also something that I didn't tell you about is that another way to recover these results is using the perspective of the symmetry TFT. And for this, it was very useful for us that like these papers on the symmetry TFT of U1 symmetries appeared. And so I won't explain this, but I just want to say that it's a nice unified perspective, because in a certain sense, the approach that I used before, so when I was studying, say, a non-invertible symmetry, I was assuming that there was no two-group symmetry for the same symmetry. So I was assuming to be in a situation in which they didn't appear simultaneously. But with the symmetry TFT, it's very easy to study the more general situation in which you have both of them simultaneously. And let me mention some open questions. So the first thing is that probably it was very clear from my talk that I relied a lot on the fact that all the theories that I studied are Lagrangian. So it's not clear like if the conclusions that we have apply also to non-Lagrangian theories. So this is something that would be interesting to investigate. The other thing is that, of course, it would be even more interesting if we manage to retain some of these generalized symmetries when we do a compactification. So probably for that, we need to do some more complicated compactification than the one that I studied. For example, like one possible first generalization is instead of compactifying on a two-sphere, compactifying on some more general Riemann surface, or maybe the spindles that Dario told us about, or I don't know. And the other thing is that in this talk, I also focus on continuous symmetries, which, I mean, it's nice. You can deal with them very easily. But so for the moment, we have nothing to say about finite symmetries. So that's something that would be interesting to discuss. Some theory that you might consider that's still not too complicated is the SQTCD, but now with SO gauge group, in which case, depending on the global variant of the gauge group, you might have two group or non-invertible symmetries, but for finite symmetries. Okay, this is all I wanted to tell you, and thank you for the attention.
So are there any questions? Yes, please.
Look to the previous improvement, the first slide, the previous one.
The previous one.
Yeah. So in the item number 1, you said there are some examples that you worked out from 5D to 3D.
Yes.
And you mentioned Seibert's theories when you talked
yes.
about it. So do they include those with the gravity dual, like with the ADS6 gravity dual, famous?
I don't think like you mean the gravity dual of the compactification.
5D stuff. Let's start with
The 5D ones should be known. I mean, I'm not an expert, so I don't know exactly, but I think the 5D gravity duals are known, but the flow from 5D to 3D, I don't think it's been studied a lot.
By a Riemann surface with topological twist, and the 3D gravity dual is known.
You're asking if it's known?
No, I'm saying it is known.
Okay. Okay.
So I was going to ask whether you have an interpretation in gravity of this.
We don't. So we focused only on the field theory side, but we have many results on the field theory side that would be nice to reproduce. Yeah.
Questions? Yes. About the fact that the universities are not equivalent, can you predict this only from the symmetry? I mean, is it just a fact that the magnetic symmetry form a two group with a level symmetry?
What do you mean they're not equivalent?
You had this sum at some point
Yes.
over these fluxes, and each of the term is a partition function in some universes.
Yes.
Partition functions are not the same but are different.
Yes.
And some of them are zero.
Yes.
I mean, typically, if we just have a universes because of a standard invertible symmetry,
Okay.
then all the universes are essentially equivalent. At most, they
Oh, I see.
have phase.
Yes.
I'm asking whether this fact is a consequence of the fact that the symmetry is in a more structure like a two-group.
I don't know about that. Yeah. It would be interesting to understand.
Because I mean, you need to know this full partition function, but it's just, I would suspect it's just a consequence of the symmetry. So you should be able to say to relate the partition function in one universe.
Yeah, maybe that answer can be obtained using symmetries. But for me, it was important to consider the full partition function because I wanted explicit Lagrangians for these theories, compute anomalies in this Lagrangian, and verify that they match what I was predicting. So, yes.
Is there an interpretation for why non-invertible becomes invertible? Can you reduce like these?
Yeah, I don't know. I think, I mean, at least in these examples, it's related to this. So in 4D, you have an ABJ anomaly. It's going to give you an ABJ anomaly in 2D, but in 2D, we know ABJ anomalies don't give you non-invertible symmetries. I don't have a deeper understanding of this fact. Yeah.
So, my question, like, if you are considering also a pseudo classification, if you consider compactification on some manifold of non-contractible cycles, do you expect any?
Yeah, what's interesting there is that you can start, for example, turning on holonomies rather than just fluxes through the Riemann surface. And so these anomalies might give you something more interesting. So that's the vague idea that I have, but I haven't looked at it. Yes.
You emphasize this fact that gauge anomalies in principle should not match along the energy flow, but
Yeah.
here they do
Yeah.
because they really give a difference in the structure.
Yeah.
But are there examples of cases in which you, for instance, a non-abelian ABG anomaly which does not give a difference in the structure, and you are able to see that actually the gauge anomaly that does not match along the energy flow?
Well, in the non-abelian case, so you don't have a non-invertible, and the symmetry just remains the same.
Yeah,
when you do.
I mean, the naive expectation that the anomaly polynomial stays the same along the energy flow, then it's false in that case because they don't give a difference.
No, in that case, it's correct because that type of anomaly just gives you a break into some finite symmetry that's still invertible, and that finite symmetry survives also in the lower dimensional theory.
Okay, but
so
you see like the coefficient mod something of the anomaly, so it might be, I don't know.
Yeah, I don't know. I don't want to to make like a super general statement. So it could be that there are cases like in which what you said happens. So.
Okay, so if there are no more questions, let's end this interrogation.